Happening. It's Mr. Gustin. I'm back in the physics classroom. We have a 3-day weekend. We didn't get the snow day we were hoping for yesterday, but I'll tell you what, it snowed a ton. But we do get a 3-day weekend and it's scheduled. Today is Friday, like I said, and today we are looking at our third kind of, I don't want to call them challenge problems, but just weird scenarios, right? Different scenarios that we have. We're utilizing our net torque equations, net force equations, maybe kinematics, maybe angular acceleration, just different concepts we're putting together as we approach the end of our rotational kinematics and rotational dynamics study. So here's the example. Without further ado, without wasting too much time, let's look at the example. The example I have today is a basketball on a ramp. And now we've done an object on a ramp before, and the object on the ramp we had was rolling down the ramp. But this time around, we're not going to roll it down the ramp. We're actually going to roll it up the ramp and let it roll back down. So I don't think I need to show you this necessarily, but I'm going to make sure the ball is rolling before it reaches the ramp. That way there's no applied force on it. Its velocity is not zero to begin with. We are only focused on the motion as the ball rolls up the ramp, the time it's in contact with the ramp, on the way up and on the way back down. So it's pretty easy. We'll just roll it up. We notice that it slows down and it comes back down. I'm going to show you that again, right? I'm not sure maybe if you've paid attention to how objects move when they're on ramps, but watch it, right? Watch what happens. So I spin this thing. When I do, I push up at a radius that provides the torque it needs to go speeding up. Once it's done though, once my hand leaves contact and it hits the ramp, it does slow down, come to a stop, and then come back down the ramp. We've seen that kind of motion before, but here we go. Rolls up and rolls right back down. One more time, watch it. Rolls up and rolls right back down the ramp. One more time, rolls up. It's gonna fall off this time because I can't aim, but you get the idea. Rolls up, stops, rolls right back down. I think this thing is warped. Rolls up, rolls right back down, okay? So, a couple things. First things first, let's just go ahead and get some graphing practice in because why the heck not? So let's graph this. Let's go ahead and graph what happens to its angular acceleration, what happens to its angular speed, and what happens to its angular displacement. We'll also go ahead and graph, might as well, acceleration, velocity, and position. All of this is while we are on the ramp, not on the flat surface, okay? So let's think. How does the speed change? Well, it was obviously moving in a positive direction, right? We can say whatever we want, right? It was moving up the ramp. And as it moved up the ramp, let's go ahead and call, if we think about the ball rolling up the ramp, this is my picture right here. This one is trash! If I think about the object and as it rolls up the ramp, let's call this direction positive, so we'll call this direction over here negative. I can think of the forces that act on it. There's gravity, there's my normal force. We gotta figure out friction. We'll figure out friction later, but I do know that it is moving this way and slowing down. And because that's the case, if it moves this way and slows down, then the torque that is applied to it must be in the opposite direction of that motion to slow it down. So this is actually where the force of friction points. It's not that complicated to think about. It's just counterintuitive because we've always been taught that whatever the direction of velocity is, friction points opposite that because that's what friction is. It's resistive force. But that's not what we have here. We don't have sliding. We have static friction. Static friction is stuck. It's sticking to the ground. What is happening? Well, as you roll this thing up, it is slowing down rotationally. It's pushing itself back this way. So my torque needs to be pointed in the direction it's being pushed, not the direction it's going. So what happens? I said it was going positive to start. After a while, it starts to slow down. It comes to a stop at the top of the ramp. That's what this is here. Top of the ramp. The top of the ramp, it's steady. It's stopped moving. Then it rolls back down the ramp and speeds up. And if I think about this thing at the top of the ramp now, there's Fg, there's the normal force. If it's going to start going from rest in this negative direction, guess where that force of friction is pointed? Oh, it's pointed in the exact same direction to speed it up. So the force of static friction is pointed the same direction, going up, going down. That doesn't change. It just is slowing down the rolling here, and then speeding up the rolling back once you reach the top of the ramp. So here is my omega and time graph. My acceleration is going to be in the negative direction the entire time, even at the top of the ramp, because my FBD doesn't change. My force of friction doesn't change. My normal force doesn't change. My coefficient of friction doesn't change. So my angular acceleration is going to remain the same the entire time. How about theta? Let's call the bottom of the ramp. We'll call this over here 0 meters, and we'll call this over here like X meters, some giant number. So up the ramp, then back down. So we start at 0, moving in the positive direction, but slowing down, and eventually reaching our stop. That's the top of the ramp, and then it turns around, changes directions, and moves its way back down to where it started. So I have this downward opening parabola for my angular displacement. I wonder how these graphs vary or look the same for both of these motions. And the fact of the matter is, folks, the only difference between these two graphs numerically is that they are my angular variables multiplied by r. That's how I get them. They're bridge equations, so their motions are actually identical. Their values for acceleration and velocity and displacement are different because of the radius factor, but their shapes are absolutely identical. So I think about which way is the thing accelerating. It's accelerating down the ramp the whole time. Negative. It's negative down the ramp the entire time, so I'm calling down the ramp negative, I guess, in this case. The velocity starts out up the ramp, moving up the ramp, slows down, comes to a stop, and then speeds up down the ramp, linearly, not rotationally, literally like goes up, stops, and comes back down. That's how the object works if I was just staring at the middle of the ball. Lastly, it goes up, slows down, turns around, changes direction, and comes back down. I get the same type of graph, this downward opening parabola. These are my three graphs. Is this the question I'm asking you? No, I'm not. But I am showing you that these two motions, the linear motion and the rotational motion, are incredibly similar. They are linked. They are bridgeable. We're allowed to use our bridge equations here. All right? These are my graphs, just good graphing practice. It's always nice to go revisit our kinematics graphs, both linear kinematics and angular kinematics. Okay? I'm going to go ahead and leave up my FBDs and tell you what the question is. My question of the day for this motion is, what is the linear acceleration of the basketball? One thing you have to know is that the I for a thin sphere like this, like a basketball, a hollow basketball, its I value is 2/3 mr squared. Okay? So this is the challenge problem that I asked you in class today. If you want to give this a shot on your own, do it. Go ahead and start and do it. If you don't want to, if you miss class and you're like, I have no idea how to start, I'll start it. I'll keep going. I'll work my way through it. All I need you to do is to try it, to at some point pause the video and say, I've got it from here, okay? So pay attention as long as you need to, but at some point pause the video, work your way through it, and then come back and check it out. The only rule I had in class today was this time around, I didn't give you meter sticks, I didn't give you the balance to use, I didn't give you video physics or a video analysis or a timer. The only tool you got today was a protractor. So I could measure, the only thing you were allowed to measure today was angle. And we measured the angle of the ramp, and it ended up being like 18 degrees. That was the angle of the ramp, not the angle of rotation. We're not talking about theta. I'm talking about literally this angle right here. This angle here, theta, was 18 degrees. That's what it was. Okay? So I'm going to start. You pause it whenever you feel like you can do it on your own, and go. So to find linear acceleration, if I think about linear acceleration, I'm going to highlight that. That way I know what I'm solving for. That's A. I don't have any time. Without time, kinematics gets really hard. So I don't know initial velocity. I don't know final velocity. I mean, I know that the velocity at the top of the ramp is 0, but that's all I know. I don't know distance. Kinematics is out of the question here. I don't have any of my kinematic tools to measure these variables. I've got to think of a different equation. So my favorite linear equation that has A in it is F net equals MA. And in this case, the forces that are acting on the basketball linearly to move it up or accelerate up and down the ramp. Down the ramp, I've got Fg in the parallel direction. Up the ramp, there's the force of static friction. Now, I chose to make gravity positive because that's the direction of acceleration. It slows down up the ramp. It speeds up down the ramp. So gravity is the force. Gravity in the parallel direction is larger than static friction. That is true. So I make gravity positive. If you don't do that, if you make force of friction positive, you'd better make MA negative because the acceleration is opposite the direction of motion. I prefer to make acceleration always positive, so whatever force is in the direction of acceleration, that's positive. Fg parallel, you're positive. Force of friction static, you are negative. So I'm here. I'm going to go ahead and expand some things. MA is equal to mg. This is parallel to the ramp. And if I think about my parallel components, now we're going back a ways. My parallel component down here, my FG parallel is opposite. I'm going to go ahead and write mg sine theta for that. I rarely write FG. FG is just not something I'm writing in February. I'm writing mg, and then if there's components, cosine or sine theta. That's what I'm doing here. Okay? Lastly, I have force of friction static. I don't know mu. I don't need to know mu. I don't know normal force. I can probably write, mg cosine theta for normal force, but it's not going to do me any good. I don't know mu. I'm going to leave it as FFS for now. And I realize I have an unknown in acceleration. I have an unknown in force of friction. I can't solve this problem. In math class, if there are two unknowns in an equation, you need a second equation. So I got to think to myself, if only there was another equation that describes this motion that includes force of friction static, and there is. I'm going to go ahead and draw kind of this line here. If this is my linear motion of the object, there's also rotational motion. And my rotational motion is dictated by my net torque expression, which is always I times alpha. And in this case, the only force about the pivot that is causing a torque is the force of friction. So I've got force of friction static times the radius. Remember, when it's a torque, it's a force acting at a distance. It's not just FF. It's not just a force. I need my force times distance. That's what torque is. And that force is acting at a 90-degree angle to the lever arm. So what sine of theta, 90, 1. I'm going to leave it alone. So now I'm here, and I've got an equation that has force of friction static. Let's go ahead and expand I. We said earlier I is 2/3 mr squared times alpha. This equals force of friction static times r. Okay, I can see that an r drops out. This r goes away. The r squared goes away. I've got 2/3 mr times alpha equals force of friction static. I can start making a substitution, I think, over here if I want to. I've got force of friction isolated. I've got force of friction isolated over here. I can isolate force of friction over here. Let's actually go ahead and do that. Add it, subtract it, mg sine theta. I'm going to have that over here. I'm going to add force of friction over here. I'll subtract MA over here. And if both of these things are equal to force of friction static, I can set both of those things equal. It's called substitution in math class. Sometimes in math class, if I have two equations and two unknowns, I would graph both and find their intersection point. Algebraically, substitution is the exact same thing as graphing on a graphing calculator. I'm going to go ahead and set these equal. I get mg sine theta minus ma is equal to 2/3 mr times alpha. Now this helps me a little bit. I eliminated force of friction static, but now I've got A, I've got R, and I have alpha. So I went from having this like one equation with two unknowns to having one equation with apparently three unknowns. Did that help me? Doesn't seem like it. This is where my conceptual physics has to come into play. I have to understand this. This alpha and this A are very closely related. The acceleration of the object is very closely related to the angular acceleration. These motions are happening simultaneously and because of each other. If it's going to accelerate angularly, it's going to accelerate linearly. this is what I would call bridgeable motion. I can go ahead and substitute alpha out. I can go ahead and make alpha A over R. I can use my bridge equation. Alpha times R equals A. Do a little rearranging. Alpha equals acceleration over R. When I make that substitution, some things start to happen. Number one, I've eliminated that alpha as a variable. Now it's A. I replaced one of my unknowns with a variable I'm solving for. What also happens is that this R and this R disappear. So I'm left with mg sine theta minus ma is equal to 2/3 ma. I'm close. I feel like I'm getting close to an answer here, but the only thing I can measure is angle. I don't know mass. I hope you're seeing this algebraically, that mass goes away. Every term has mass in it. Not just every term has mass in it, every term has the same mass in it. The mass in these terms is the mass of the basketball. If we're talking about a bucket, pulley, a two-body system, this might not be the case. But because this is the same object in both equations, we're discussing the exact same object linearly and rotationally, this mass term disappears. I am now left with g sine theta minus a equals 2/3 a. This is what I have, and now I get into this weird adding of fractions thing. G sine theta minus a equals 2/3 a. Stick with me. If this is 1a, it's technically 3/3 a. 3/3 a plus 2/3 a equals 5/3 a. This is what I have. At this point, if you have not paused the video to finish it, just do it. Pause the video, finish this thing yourself, come back and check out the answer. As I algebraically do this, I'm going to go ahead and bring 5/3 to this side. I do that by taking the reciprocal. I multiply by the reciprocal. I'm going to move over this way now, so I'm not writing too low on the board. I get 3/5 g sine theta is equal to a. Do I know what that is? I certainly don't. So I'm going to have to grab my calculator over here, make sure my calculator is in degree mode, and do 3/5 times 9.8, which is g, times the sine of 18 degrees, which is what my angle is, of the angle of the ramp is, and I'm in degree mode. My answer ends up being 1.82. 1.82 meters per second squared is equal to my linear acceleration. If I was going to derive an equation, there's a great derived expression. If I want to solve the equation, here's a great solving of the equation. Most often this thing ends up as a deriving equation, but I asked you specifically, what is the linear acceleration? Not deriving, what is it? What is it? It's 1.82 meters per second squared. Able to do so because this object is moving both linearly and rotationally, and I can rely on both my knowledge of linear and angular motion to solve this challenging problem with the only tool of a protractor or an angle finder. Okay? That's all I've got for you. If you got questions, drop in the comments. If I screwed something up, drop in the comments. Send me an email. Talk to me in class. Until next time, see ya!